Hey guys, welcome to the video. I'm really sorry about the delay. I had a very important talk with my manager about the future of all things that I do, I teach, and it was super urgent to speak about these things, so I had to come late a bit. Okay, so let's start because I don't want to waste any more time. I am really hopeful, really hopeful that we will be able to finish the microservices classes today, because what we need to cover is API gateways, internal communication, and we need to cover uh, disasters and some other small topics. I'm not very sure that we'll be able to finish it, but maybe this or the next lesson will be the last, because part of the lecture includes Docker and Docker Compose, and I already did a video on Patreon about Docker Compose, so we don't need to cover that. And I'm currently doing and recording a video about Docker in general, so I'm going to cover everything around Docker on Patreon, so we don't need to actually cover it in these classes right here about the microservices. So hopefully we will be able to finish everything today. I really hope so. And if we don't, then we will have another class later this month, I believe in 2-3 weeks. And then we may say that everything around the microservices is finished. Good. Well, of course, we can do some other topics like Kubernetes and deploying microservices on Kubernetes, but that's for another time. So, what I want to talk a bit is a little bit of summary about the last time. Last time we talked about some types of querying the services, how to communicate from our clients to the servers, and there are some approaches, but most of them are, for example, the most widely used scenarios are actually direct server client to server communication, when the client directly calls some of the servers, and the server side rendering, which means that we will have a separate front-end app with a separate server. The client will call that server, and this server will communicate with the microservices. I showed that in our demo app. If you don't remember, we have two applications. The one is completely finished and it's completely working microservices app, and the other one is experimental. The experimental one just has a little bit more things considered. For example, another microservice called schedule, which is not finished, totally not finished, and an API gateway. So we have a little bit more concepts written in this demo. So depending on the scenario, you may choose to take a look at one of them. Good. So the most widely used scenarios are direct client to server communication and server side rendering, but from time to time we need to have real-time communication, especially when the business logic forces us to do so, or we also may need to have an API gateway. The API gateway is a separate concept which is super important if we want to introduce cross-cutting concerns, or if we want to introduce various aggregations of our queries. So last time I talked about the first two, and now I'm going to continue with the API gateway. Good. So let's start with it. The API gateway is another form of communicating with the server when we have microservices as an architecture. So what's the deal with the API gateway? Instead of having multiple microservices, something like this, for example, a microservice, application spread among 4 microservices, for example. We have server 1, server 2, server 3, and server 4. Then we may have a client app, some browser. And the easiest way to communicate with all these microservices is just for the client to call these servers. This, and this. Well, that's super easy because it's a typical HTTP request. It's nothing uncommon, so to speak. But the problem here is that the client may need to introduce additional business logic because the client may need to render some data from server 1, which joins with other data from server 2, and then we may need to render something from server 3. So the client may need to render and aggregate data from the microservices, which means that the client may need to introduce additional business logic. And the client is responsible only for presentation. So if we start introducing business logic in the client too, we will have business logic spread among both the servers and the client, which is not always that bad, but depending on the business requirements, you may have lots and lots of complications because of this particular thing, of this particular scenario. If you have the client aggregating the data from all the different microservices. So the second approach is to have all these microservices here, server 1, server 2, server 3, server 4. You may have the client, but instead of calling every single microservice directly, you can introduce a middleman here, and this is called the API gateway. This is an API gateway. And this is the middleman who calls these servers and aggregates the data. And the client only knows about the API gateway. So in this scenario, the client does not understand that there is actually a microservices application behind the app. So the client only calls the API gateway. So this may look a bit weird because you may say, well, what's the point? Isn't that a bit monolithic? Well, not exactly, because you can easily scale different services and you can easily replicate this and replicate this. You can also easily replicate the API gateway behind the load balancer too. You will have all the data aggregation happen on a single place, and the client just needs to fetch the data and visualize it. And this is exactly what clients are for. They need to visualize and they need to present the data. They do not need to introduce a lot of business logic. Of course, that's not always possible, but we should aim for that. Well, there are some negative sides of the API gateway, because with the API gateway we may have a problem in terms of performance. We may have so many aggregations in the API gateway that we may introduce a bottleneck there. So we need to be careful. The other positive side of using an API gateway in front of your microservices is by using API gateways, you will have all the cross-cutting concerns of the apps right here. For example, authentication, JWT parsing, for example, SSL certificates, and so on. So caching and many more. So lots of the cross-cutting concerns which will be used in all the microservices will be transferred to the API gateway, which introduce what? Single responsibility. And another positive thing of introducing microservices is that you will have less surface area for attacks. Let's say that somebody wants to throw your application down. He only sees the API gateway as an external service. Everything else is in an inside network. And you may say here that introducing an API gateway introduces more communication and more latency. Yeah, that's true, but consider the following. Let's say that all our microservices, service 1, service 2, service 3, are in an internal network. These are closed. So calling from the API gateway to the server 1 will be super fast. Let's say 0.1. Calling here will be 0.1 and calling here will be 0.1. So it will be super fast. And calling from the client to the API gateway will take, let's say, 0.6. So because the client is part of an external network, we need to communicate over the internet. So the total time of requesting the whole site will be around 1 second, because we will have 3 0.1 calls and 1 0.6, which is okay. It's not super fast, but these calls are these times are just for educational purposes. And let's say that we have the opposite scenario. We don't have any API gateway. We just have server 1, server 2, and server 3. Then the problem is that the client needs to call server 1 for 0.6 seconds, needs to call server 2 for 0.6 seconds, and needs to call server 3 for even more, 0.6 seconds. So the total time will be around 2 seconds this time. So even though we have a middleman, because our middleman is part of the internal network, the middleman is completely okay to be there, because it doesn't introduce so much overhead, and in some scenarios it doesn't introduce overhead at all. It depends on the case. It depends on the case, because I'm not saying that this will be your typical scenario and that if you don't use API gateways, everything will be twice as slow. No, this is just an example, because you may need to just call a microservice and nothing more. So let's say that you have the client, you have a server 1 here, and the client may need data only from a single microservice. Then this will be 0.6. And if we have the same scenario through the API gateway, then we will have 0.6 to the API gateway and additional overhead to the service, to the microservice. So it's not the best scenario to have API gateways always, but still it's a good pattern and you should consider it every time you do microservices. Don't introduce it just as a golden hammer. Don't introduce it as something that will be used everywhere on every single microservice and in front of every single app we produce. No. Use it only if you see that you will have to transfer a lot of business logic in the client, and don't use the API gateway in front of every single microservice in your app. Use it where it's appropriate, when you need data aggregation. So the whole idea in terms of theory, because I already talked a lot about the API gateway, the whole idea is that it provides single entry endpoint for a group of microservices. It's like the facade design pattern. You will have a single entry point in front of a lot of complexity, exactly like the facade design pattern, which is also known as backend for frontend. So that if you happen to hear about backend for frontend, it's essentially the same thing as the API gateway. You just build the API gateway for the specific client needs. And if you have multiple clients, for example, you may have web apps, you may have mobile apps, you may need to introduce multiple backends for frontends. And the API gateway just acts as a reverse proxy and a man in the middle between all the clients and the microservices, which allows you to introduce all the cross-cutting concerns: authentication, cache, SSL certificates, and many others. So this allows you to concentrate on the business logic on the different services. Otherwise, you may need to introduce all these cross-cutting concerns everywhere. Let's take a look. Let's take a look and see. We can see that in our app, we don't have an API gateway by default. So every time we need to add a web service, we need to add token authentication. So every single web service here, it doesn't matter which one of these, without an API gateway in front of it, it needs everything. It needs application settings, token authentication, health checks, automappers, and so on. So if we have an API gateway, we may have to skip some of these. For example, the token authentication. There is no need to check every single request for tokens and for authentication logics if that is extracted to the API gateway. That's super important here. So the API gateway may serve as all the common functionality for all the microservices. So here it is. Here is an example using a single custom API gateway service. A single custom API gateway service. Let's take a look. We have different microservices here. Let's change the color. We have different microservices here. And we have an API gateway. All the client apps call the API gateway. We may have server-side rendering up here. It will call the API gateway too. So it's important to understand that no client will directly call the internal microservices. As a matter of fact, these microservices here are not exposed to the internet. They are not exposed to the internet. So they're just part of an internal network, and the public part is only the API gateway or the front-end server-side rendering apps, if we have any actually. So consider that and make sure that all the API gateways are actually relevant, because we don't need to introduce them just because we want API gateways in our app. That's ridiculous. Because if we are not very careful, let me just check how is the connection. The connection looks great and everything looks fine, so I'm going to continue. So the important part here is that if we're not careful with the API gateways, they may become a full monolithic app. They may have a lot of endpoints, they may couple the microservices, and you may destroy their benefits. So API gateways should be considered carefully and should be considered as separate services. So you can easily introduce multiple API gateways. You can segregate them. So at first you may have a single API gateway for each client, but you may then split them by logical groups. Everything depends on business boundaries, so I cannot give examples here because it depends on your loads, it depends on your concurrent users, it depends on your overall architecture, and it depends on lots of things, lots of things. So consider them as a helpful tool, but do not introduce them everywhere. Here are multiple API gateways or backends for frontends. Here you may have two apps, one client and one web app. You may have a traditional web app which has server-side rendering. That's completely okay. So you have a single front-end for backend, client mobile app, and a single front-end for backend, Quant web app. These communicate with all the microservices, but these provide separate presentation models for the different clients, because typically a client app will have different entities than a web app. So it's completely normal to have different API gateways. It's completely okay. What are the benefits? I already mentioned some of them, but we're going to talk about them a little bit more in detail right now. So first, it's a reverse proxy and routing. The API gateway gives you routing, gives you a single point of entry, which is quite quite a good advantage in terms of networking and in terms of hiding internal complexity. So it easily decouples the client, can easily modernize legacy monolithic apps, and can hide the internal microservices. So this reduces the area of potential attacks. You have request aggregation, so you can easily aggregate different parts of the data, which reduces chattiness between clients and microservices. And this is especially important for remote applications. Super important for remote applications, because when you have applications which communicate over the internet, request aggregation will help you reduce the separation of the business logic, because you don't want to have a business logic on the client and on the servers. It's better to have the business logic only on the servers, and the client should be responsible only for presentational purposes. Of course, that's the theory. In practice, it's not always the case, because sometimes we may have additional complexity, but we should always aim for backend microservices, for business logic on the backend microservices. We will have offloading in terms of code, because authentication, load balancing, retry policies, response caching, IP whitelisting, and all other cross-cutting concerns will be part of the API gateway, and you will not see them anywhere else, which is actually quite good. You have a single place where to put all this infrastructure code, so to speak. What are the drawbacks? What are the disadvantages? Well, first, you will create bigger coupling with the internal microservices. So when you introduce an API gateway, you will have internal coupling, which is not that bad. It depends on the scenario, and it depends on how you couple all these things. You will have an additional point of failure. So if the API gateway fails, but the microservices are online, then your app will not work. So you will have one more application which you need to monitor and which you need to have logs on it, and it's an additional point of failure. You have additional network calls, and like I said earlier, because I draw the different scenarios. Like I said earlier, these additional network calls are not adding a huge impact, because you don't make calls over the internet. The API gateway is part of the internal network of the other services. So communication between the API gateway and the microservices will be super fast. So you will not have a lot more overhead from the additional network calls. It's completely fine. The API gateway may become a bottleneck, so you may need to scale it independently of the microservices. And of course, introducing yet another app introduces additional development costs and maintenance. So this is actually not so great. This was everything about API gateways. You have various options to use API gateways. You can go to Ocelot, C#. Ocelot is a tool for creating API gateways. It gives you a lot of features, a lot of things you can use. You can easily install it, you can easily use it, and you can easily introduce it to your apps. The only problem with using Ocelot or any other external tool for your API gateway is actually that you don't have full customization and full control. The tool is great, the tool is working great, the tool is perfect for your basic scenarios, but from time to time you may need to actually introduce your own microservice as an API gateway, like I did here. Here it is, the API gateway is just another ASP.NET Core app. It has the same things, it has routing, JWT authentication, and like the server-side rendering, it uses the so-called Refit client. I talked about it in the last video, so you can take a look at the last lesson if you're interested about Refit and about what it does, but essentially it allows you to call other microservices very easily. Here it is. For example, this particular API gateway has a single cards controller which needs to fetch all the car ads in the system which are mine. So what we need to do is we need first to get all car ads which are for specific users from the dealers backend, dealers microservice. Then we fetch the IDs, and because the carrot output model adds not only the carrots but the views for the carrot, and the views for the carrot are part of the statistics service and the carrot details are part of the dealer service, we need to communicate with both of them to fetch the data. We need to aggregate the data. So it's a perfect scenario for an API gateway because it can fetch parts of the data from here and parts of the data from here. And then it can aggregate them, like here. So first we fetch all the car ads, then we get the car ad IDs, and then fetch from the statistics microservice all the car ad views for the specific IDs, and then we map the data and map the views and populate the data. So we aggregate the data so it will be presented for the client the way it expects. So here we have the API gateway communicating with two other microservices through Refit, the easy REST client, and it calls the dealers and it calls the statistics microservice to aggregate some data and combine the data for a single view model. We use Refit, so all the services just specify how to communicate with them. Here it is, and here they are. And this is part of the Refit functionality. We can easily send a query string for this. And the services know how to communicate with each other by the Docker Compose. Because when we go, we have something along the lines. Let me find the admin. So it's not complete here. So let's go to the other Docker Compose, and we can easily see how we specify the service endpoints, like here. And if we go to app settings, we can see that the service endpoints are here, and we can easily transfer that to the Docker Compose file. So pretty much this is the API gateway. It's nothing special, it's yet another app. It may introduce cross-cutting concerns like token authentication, and it can easily just call various microservices by using Refit clients like here. It's super easy to set up an API gateway. So you can use Ocelot if you like, but for more advanced scenarios you may need to write your own API gateway. Good. So next is real-time communication. Real-time communication can be achieved with HTTP WebSockets with some fallback mechanisms to normal long polling, for example, or other mechanism. Usually real-time communication is used only when you want to push data to the clients directly. So you have ASP.NET Core and SignalWire as a real-time communication technology. So if you are using ASP.NET Core, then you use its real-time communications. So here is a diagram showing how this works. So push and real-time communication based on HTTP. We have a backend with a SignalR service hub. If you're not familiar with SignalR, I have a video about it, just look it up. But I've explained how SignalR basically works. And SignalR allows you to open a socket for duo communication. So you can easily send messages from the client to the server and vice versa, from the server to the client. That will be super easy. So you can have multiple clients connected to that hub, and you just need to send the data to the client, and the client will be responsible for visualizing it. Before moving on to internal communication, I would like to show you how I've implemented, but not in the experimental features, but more on the normal code. And I'm going to also open the client here. So the logic is like this. Every time a new car is added, every time a new car is added to the system, we want to send a notification to our clients saying that, hey, a new car was added. So how to do that? First, we need to somehow, when we add a car on the car adds controller, we need to somehow send an event. We're going to talk about events in a bit. We need to send an event saying, hey, a new car ad was added. So we create a car ad created message, we populate it with some data, and we send that data to the other microservices. Okay, we're going to talk about this internal communication in a bit, but we have a separate microservice, which is purely only existing for sending notifications. This is the notifications microservice here. It is just a normal ASP.NET app with token authentication, with health, with messaging, and of course SignalR, because we want to use SignalR as our notification hub. And we just configure the origins for cores, and we map some SignalR hubs like the notification hub. It's available at /notifications. So this hub right here, every time we receive a message which is called carrot created message, we are going to talk about the iConsumer interface in a bit. Every time we receive a message from a carrot created message, we just want to send to all the clients that are currently authenticated, that are currently available, we want to send that message, and then the client is responsible to visualize it. Of course, you need to be familiar a bit with SignalR, but SignalR, most importantly, has the so-called hubs. All these hubs have real-time communication functionalities to the client. So here, every time a new client connects to the server, I'm just checking whether it's authenticated. If it's authenticated, I add it to a group of authentication users. And every time the client disconnects, I remove it from the group. And every time a new car ad is added to the system, I'm receiving a message that the car ad is created. And then I'm just saying all the clients in the authenticated users group, just send them a notification about the created notification. It's super easy once you understand how to create different SignalR hubs, different communications, because like you see here, the configuration of the notification service is not a lot of code. It has some JWT configuration. This is based on the Microsoft documentation, so it's pretty much copy pasted from their code. We have a notification hub to validate what happens when a user is connected and an actual authenticated user is connected, and we have the hub calling all the other all the web apps in the group. So it's pretty much easy peasy. Of course, you need to understand SignalR, but I'm not going to talk about SignalR in details. I'm just going to talk to say that you can easily add it to your microservices app, and you can easily visualize various notifications or other real-time communication. If we go to Visual Studio Code, we can see that in the Angular app, we will have in the shared folder the notification service. So the notification service is pretty much this. So this is everything you need to add to your code to make SignalR work. Here it is. We have an option to authenticate, and we have some connections to the actual server, and we say when we receive notification, alert some success message. It's super simple and it's not very advanced. So if you want to introduce real-time communication in your microservices, this is the approach. You may have a single microservice responsible for notifications and real-time communication, and you send messages every time you need to visualize something on the client. Good, so this was real-time communication, and I want to create and make some summary, a little bit of summary here, how to query the services. First, we have direct client to server communication, then we have server-side rendering, then we have an API gateway, and then we have real-time communication. These are the most commonly used scenarios. Direct client to server communication happens when the client directly calls the microservices. The server-side rendering happens when we don't have a SPA application and we have a backend which calls our microservices. We have an API gateway which allows us to aggregate the data and not introduce business logic on the client. And we have real-time communication which allows us to send push notifications to the client. So these are all the various communications when we want to query data from the microservices. But actually these approaches, the client to server communication, these approaches in different scenarios are not that problematic in terms of microservices. The most problematic scenario in the microservices world is a business operation, a business process that spans multiple microservices. When you want to create data and the data spans multiple microservices, this is the problem. This is a bit more problematic, and this is when we're going, and right now we're going to talk about that. We're going to talk about internal microservices communication. So Let's take a short break of 10 minutes and we're going to continue with internal communication. so let's continue. We need to talk about internal communication. Next is internal communication, and first we need to describe all the different communication types which may happen in the microservices world. First, we have synchronous and asynchronous. The synchronous call is through HTTP. Why it's synchronous? Because when you make an HTTP call, you need to receive a response before continuing with your logic, because HTTP is a request-response protocol. So you send a request and wait for the response to happen. Sorry. And if something is taking longer than expected, for example, let's say something like this, we may have a single service here and another service here. What will happen if we have service 1 calling through HTTP service 2? And the service is, let's say that service 2 is not responsive, so it takes a while. Well, service 1 will be unresponsive too, because the client waits for service 1, the service 1 waits for service 2, and service 2 is not available. So everybody through the chain is waiting. Service 1 is waiting and the client is waiting. So this is why HTTP and HTTPS communication is actually a synchronous communication. Then we have asynchronous communication, which is usually by using message queues. So asynchronous message queue protocol, this is what AMQP stands for. And here the client usually don't expect a response. It just sends a message and that's it, and it can continue working with something else. So the same situation here will be if we have the client, the service 1 and service 2. Client calls service 1. Service 1 sends a message to service 2 but does not expect any response. So service 1 returns the client with some data. And this means that even though service 2 may be irresponsive and may not be available right now, the message will be delivered later when the service 2 microservice is back online. So this message will eventually hit to service 2, but the client and service 1 are still available because they don't wait for any response here. So with asynchronous communication, the client usually don't expect any response. Then we have single or multiple receivers. Single receiver is typically the command pattern, and multiple receivers are the publish subscribe pattern. The publish subscribe pattern means that people subscribe for a message, different microservices subscribe for a message, and when a single message is sent, every single subscriber receives it. So microservices usually use a combination of these communication types. Some piece of advice here: if possible, don't depend on request-response communication between the microservices. All internal microservices should not have HTTP communication between them. So HTTP communication is okay when you have client to API gateway communication, API gateway communication to microservice, and nothing more. So this is completely acceptable, but never do HTTP communication between microservices, because you will create a distributed monolith this way, because all these HTTP calls will create a bottleneck sooner or later. So always consider the rule of one hop. The rule of one hop means that if somebody creates if some client creates a request like here, you have maximum at most one additional request to create and nothing more. So you can make multiple requests from here, but you cannot create 1, 2, 3 requests like this. So, like I said, microservice to microservice communication is not a valid way to it's not a valid way to use HTTP. It's not a good idea because it breaks the whole loose coupling of the microservices, because introducing HTTP and waiting for responses will introduce couplings. So always consider these rules. Here are some of the patterns. When we have synchronous communication, what will happen if we have the client calling the basket service, calling the ordering service, calling the catalog service, calling some other service? And if the other service is not available, you will have a bottleneck, and all of these will not be available because all of these will be waiting for the other. And waiting for the other means that the client will be also waiting for the data from the basket, and your whole application will be frozen. The asynchronous way is by just sending messages and not expecting any responses. Like here, the client calls the basket returns some response, but in the meantime sends some message here, this sends some message here, this sends some message here, this sends some message here, and so on. So messages allow you to asynchronously send something and forget about it. Pretty much messages are fire and forget and nothing more. So that is actually a very, very, very good way to use as a communication between your microservices. Here we have an asynchronous, but this is not used widely because we may have HTTP polling between services, and this pretty much does the same thing like here, but is more old school way to do it. So this is just the same thing like the asynchronous communication, but with a little bit of HTTP hacks and workarounds. So the asynchronous way uses the so-called message bus or service bus or event bus. These tools, which are service bus, message bus, event bus, all of these are actually message queue also, all of these are actually the same thing. You can just send a message to it and it will be delivered. Communication patterns here. So first, don't rely on request response if that's possible. So don't rely on that. And if you need data from another microservice, consider duplicating the data. It's completely okay. And if your microservice needs to invoke an action in another microservice, well, you can do it asynchronously. And you can use any protocol to transfer the data, and this will create eventual consistency. You just don't have to create synchronous dependencies. And what it means to have eventual consistency. Let's say we have service 1 and service 2 with some databases here. And service 1 is called by the client. The client stores some data to the database here, but it needs to store some additional data on service 2. So what will happen is that we will have an event bus or message queue or service bus here, for example RabbitMQ, which will allow you to you just send a message to the message queue, and the message queue is responsible for delivering this message sooner or later. So service 1 just sends the message and forgets about it. It can easily return a response to the client. And the whole idea here is that sooner or later this message will be delivered. So even if service 2 is not available at the moment, this message will be delivered later when service 2 is back online, which means that eventually the data will become consistent. That's the important part here. So eventually the data will become consistent and it will be added here. So first, let's see HTTP and REST. So HTTP and REST is suitable for UI needs and fast responses. So usually it's used only for queries. Your client app calls the API gateway. The API gateway calls the catalog microservice, and the API calls the basket microservice. All of these happen with HTTP requests and HTTP responses. Then we have WebSockets. WebSockets are suitable for real-time UI data. So you need to send some push data. And then we have asynchronous messages. Asynchronous messages happen usually on commands when you have create operation, update operation, or delete operation. What you do is when you have to propagate different changes throughout multiple services, then you need to use asynchronous messages. This is the best approach. You have eventual consistency and event-driven communication. So a client sends a message and do not expect a response. Every time you need to send a synchronous message, you just send it and forget about it, and that's it. And if the service needs to return a response, it just sends another message. So dual communication is also possible, but nobody expects that to happen by the typical request response scenario, in which we need to wait for the actual response to happen. So usually this is sent asynchronously through asynchronous message querying protocol. So the preferred infrastructure here is a lightweight message broker. Message broker, service bus, message queue, event bus. It's the same thing. And this is a tool which allows you to send data from one service to another, and this message broker guarantees that the message will be delivered sooner or later. That's the whole idea here. So pretty much we have tools like RabbitMQ, for example, or some cloud-ready service bus. You may use Apache Kafka, but Apache Kafka is quite advanced. So for simple scenarios, you can use RabbitMQ. It's easier to set up, it's very fast to use, and like here in my code, running a RabbitMQ instance is super easy. We just have a container, a Docker container running RabbitMQ on a specific port, and we have a volume to store the RabbitMQ data if it gets restarted. And from there, it's very easy to be introduced in the system, but I'm going to talk about that later. So the rule for communication is use HTTP for client or API gateway or first microservice level. So HTTP is only used by one hop. You call the API gateway and you call a microservice from the API gateway. So the API gateway always uses microservices. But then if you want to use a microservice from the microservice, then it's pretty much asynchronous messages. So here it is when we have a single receiver. You receive a message, you receive a request actually. The basket microservice gets some data here and sends a message and forgets about it. It's asynchronous. Then this message is delivered here sooner or later and it's stored in the database. This is the whole idea. And multiple receivers are again The event bus allows you to have a publish subscribe channel, which gives you the whole idea of publishing messages and multiple consumers receiving them. So we have some user profile microservice here. The user profile says update the user. So there is a database update here. We update the user. Then the user is updated and a message is sent to the event bus. The message is sent to the event bus, and every consumer which subscribes to this message will receive the message and can do something. For example, update the database's cache or store some other data here, but all the consumers will get data from the event bus, and this is the important part here. So we have a middleman responsible for delivering messages without any response. We just fire and forget them. We publish the message and forget about them, and that's pretty much it. So we send the message and mind our own business. We are sure that the message will be delivered sooner or later. What are the problems with asynchronous messages? Well, first, the operation is not atomic. So what will happen if network fails? What will happen if you store the new data here, but then you are not able to send the message to the event bus because the event bus is not available? Then the data will be stored, the new data will be stored here, but the data will not be sent to the other microservices, and you will have invalid state. You will have the new data here and the old data here, which is a problem, and we need to make sure that we have some process which save us from this problematic event. So what are the possible solutions here? The possible solutions are first transaction log mining. So you log the database, you mine the logs of the database and apply the same scenarios to the other microservices. This is super bad because it creates coupling to the database, to the external database. I don't advise using transaction log mining. You can use the event sourcing pattern, but the full pattern requires serious re-architecting. Event sourcing pattern actually does not store the data in the classical format, but it stores the history of data changes. So you can easily revert back or see the history, which is good for certain scenarios. For example, banking statement, in which you can see the history of all transactions, but it's very hardcore to implement for a typical web app. So the event sourcing pattern should be mixed with all the other approaches, and for eventual consistency in the microservices world, I don't think that event sourcing is the best approach here. And if you're not familiar with event sourcing, you can write down a comment and I will create a video about it. So there is another possible solution, which is the outbox pattern. The outbox pattern just creates a separate table which holds the events, and these events are part of the transaction. So with the outbox pattern, we will have a database table which stores all the messages and marks them as sent. And if we happen to have a message which is not sent, we're going to try to resend it. So if the event bus is currently not online, we can easily send a new message from this table. I have that implemented in the code, so we're going to see it. So how to achieve atomicity when we have asynchronous messages? How to make sure that our messages are going to be delivered? So first, we need to create an additional table which will hold our events, our messages between the microservices. And every time before we publish a message to the event bus, we're going to create a local database transaction, and we're going to update the current entity we're updating, and we're going to save the event as pending. So we're going to save the message as pending. Then we're going to publish the event to all the other microservices. So we're storing the message in our database and we try to publish it. If the publishing is absolutely successful, we just mark the event as completed with a new transaction to the database. And we will have a background job to check from time to time for pending events which were not sent, and we're going to publish them to the event bus. This will guarantee that we will have eventual consistency sooner or later. This will guarantee that sooner or later we're going to publish the message. And of course, we need to make sure that the database is online too, and we need to make sure that the database is also protected. The receiver microservice from the other end of the communication needs to do one of the following. The receiver needs to make sure that the operations can be performed multiple times without affecting the result, or needs to recognize duplicated messages and discard them. So how we can do that is we can do idempotent messages. So the messages should be like set the price to 40 instead of add $5 to the price, because setting the price to 40 means that even if we do it twice or 3 times, the price will still be 40. But if we add $5 to the price, if we have duplicated messages, then that's a problem, because the first time we may have the price to 40, but for duplication we will have the price to 45. And if that is not possible, we can recognize different events by adding a GUID to these events. Or we can use the infrastructure's built-in features. It doesn't matter. Here is all of that shown as a diagram. So we have a catalog microservice, and we want to update the product and send a message to the basket microservice to say that the product was updated, and we want to update the client too and update the basket in the microservice, in the database in the basket microservice. So every time we update an item in the catalog, we need to update this database too, and we need to raise a notification to the client. Good, so we update the product and send a message to the event bus. But what will happen if the event bus is not online? And that's the thing we want to store here. So we're going to have a messages table which will store our event. It will store the event type, the event body, a state, an ID, and so on. We're going to update the product and insert the message as a single transaction. So no matter what we do, if we update this database here, this table here, the product table, then the message will be stored here because everything is in a single transaction. So that's important. We need to have a transaction here. This transaction will allow us to store the message in the database, and this message will be, we can easily then analyze the message and see whether it was sent. Then what we are going to do is we're going to try to send the message to the event bus. If we succeed, we can mark the message here as successful. Great. And we forget about it. But if the event bus is not online, then we will have a background worker which will constantly poll the database, and it will try to find pending messages which are not successful. All these pending messages will be published again to the event bus from time to time, and if we successfully publish it, then we're going to mark it as successful. This means that sooner or later, even if the event bus is not online, When we bring it back online, the event bus will sooner or later receive this message and send it there. Of course, because of this background worker sending messages, this may introduce a problem here, because some of the messages may be sent twice. And if we want to make sure that the messages are not received twice, we may add an ID here and validate them in the microservice basket, or use messages which can be easily duplicated without affecting the state of the data. But this is essentially the outbox pattern. We create an outbox table which serves for sending the messages. And you have two approaches here. You may try to publish the message here, and you may only have a background worker which will poll the database. It doesn't matter. So the background worker needs to poll the database and send the information to the event bus, but nevertheless you can still try to publish it directly before trying to have it published by the worker. And this is the outbox pattern, and this is super important if you want to make sure that your asynchronous messages are atomic, and if you want to make sure that you have eventual consistency implemented correctly, because this means that eventually, sooner or later, the data on the other microservice will be updated. So I'm going to show you now how to implement all of that. So in the carrots controller, we have a message sent to all the other services. First, we need to have a message bus. The message bus is registered in the startup. We say add messaging here, and this is the code. Add messaging essentially uses a library mass transit to communicate with the RabbitMQ tool. This is pretty much coming from the documentation, and we're just trying to communicate with the host, with the RabbitMQ host, with some username and password. Then what we do here is we add some additional tables for the so-called hangfire, which allows us to make polling and make background jobs. So in the messaging method, we create a connection to RabbitMQ, and then we create a polling background job to poll the database. So essentially, take a look at all these the code here, so that you can know how to create and connect to the RabbitMQ and create the additional outbox pattern. We can easily see that we have multiple databases. Here is the default database, and here is the cron jobs connection. The cron jobs connection is actually a database for background jobs. This is why we have a separate hangfire database here, which is created by a SQL command. Okay, so we use RabbitMQ as a message queue. Mass transit is a library which helps us connect to the message queue, and we use hangfire for background jobs so that we can call the database from time to time. Good. So this is just for setuping the infrastructure. From there, it's quite easy to use and to make the outbox pattern. Here is the background job, which is called messages hosted service. It receives recurring job manager from hangfire, which allows us to schedule recurring jobs, and it receives the ibus publisher. The publisher is responsible for sending messages to the RabbitMQ instance. So this comes from Mass Transit, the library for communicating with the event bus, and this comes from the Hangfire library. So when we start the background job, we just say, well, I want to get the DB context, I want to connect to it, and I want to set a background job executing from time to time. You can find this cron job syntax online. Cron job syntax. And this means every 5th minute, pretty much. But you can easily create every 5th second because we have multiple, more than 5 stars, so it's pretty much, this means every 5 seconds. This is a cron job for every 5 seconds. So every 5 seconds we are going to check the database for pending messages and we are going to publish them. And here is the pending message. The pending messages are just get me the database, get me all messages which are not published, order them by IDs, and try to publish them by using the publisher. Here it is, this publisher.publish. Then we mark the message as published and we save changes. So this message data is part of the database and it stores the serialized date of the message, it stores the type of the message and stores whether the message was published. And we have some JSON conversion going on. So in a nutshell, the message hosted service is just trying to call the database every 5 seconds, tries to find pending messages and it publishes them. That's it. In terms of our controllers, we use these messages like this. We have a typical ASP.NET controller. We have a method which wants to send a message to RabbitMQ. We need to inject the ibus. Ibus comes from Mass Transit, which is the library used for calling RabbitMQ. And what we need to do here is we need to do our own logic for the microservice. Then we create the carat. Then we create the message. For example, we send carat ID and carat manufacturer name, model and price per day. We create the message with that data and we store it in the database together with the carat. So in a single transaction we store the carat and the message. Then we publish that message. And essentially this is the first part where we store the message into the outbox table. This tries to send the message to the event bus, RabbitMQ in our case, and this marks the message as published. So if this fails, if this throws an exception, the database will store the message and it will be sent by the background job sooner or later, and it will be marked as published too. So this is how we use this. And again, we try to make sure that all the messages can be duplicated, because from time to time we may have duplication because of the published here and the background job trying to get all the pending data before we mark it as published. So from time to time we may get a second a duplication, but that's completely fine. Okay, so that's the outbox pattern. I suggest you take a look at the code and analyze it. Make sure you take a look at all the common parts of the code, the background service, the messages, the additional database, and so on. So we reached other considerations, avoiding disasters, and in my opinion, we should finish the lesson for now because otherwise it will get too long. I'm going to, so as a summary, we talked about API gateways, we talked about real-time communication, and we talked about internal communication. So we talked about mostly communication, but this is the most important part of actually creating microservices. Make sure you take a look and remember how the outbox pattern works and what's the whole idea behind it. And then finally, make sure you you analyze the code and see how everything works together. You can also start the web services. You can turn off the RabbitMQ instance. You can try to send a request, then turn on the RabbitMQ instance and see whether the message is delivered even though the message bus was not online, and so on. Next time we're going to talk about final considerations. We are going to talk about how to avoid disasters, and I'm going to create a summary of the application and the code in general, so that you can easily understand the various tiny details in terms of the code. Good, so that was it for today. I hope you enjoyed the lesson, and I'm going to see you in 1-2 weeks when we finish the whole microservices concepts thing. Bye for now.